we start this afternoon session ensuring the quality of measurement for mass spectrometry assays. Is there anything special? With Professor Michael Vogeser, that talked also this morning. It is a physician and famous on his involvement on the measurement of small molecules on mass spectrometry. And the talk will be quality systems for commercial and lab developed mass spec tests. Is there a difference?
Thank you very much for the kind introduction, for the invitation. It's really a honor, pleasure. Thank you very much. Yes, the topic, the invitation was connected with a question I should try to answer. Is there a difference between the quality systems required for commercial tests and laboratory developed mass spec tests on the other hand? My disclosures here, and that's where I'm from, my hospital in the southwest of Munich. And I'm working there for more than 30 years now. We are running a mass spectrometry unit. You've heard about this this morning already, with at present 10 technicians trained on mass spectrometry, running 8 instruments. I've implemented this technology in 1999. And our main focus, as you have heard already, is on therapeutic drug monitoring. Mass spectrometry is a part of the technology portfolio of laboratory medicine from the 1970s on. GCMS at that time as technology for reference measurement procedures used in toxicology for very specialized metabolism testing, and it was used in, let's say, niche laboratories, few laboratories per country. This has changed from around 2000 on, where atmospheric pressure ionization coupling to mass spectrometry was implemented, and from this on, in a growing number of laboratories, mass spectrometry is applied, and this is related to highly specialized, high complexity clinical laboratories. There's a continuous growth in application, but the use is still limited globally, in a global perspective, to a rather few low number of laboratories. While the applications were initially exclusively laboratory developed tests, kit solutions become popular now, at least in Germany. They are available from a growing number of suppliers, and they are used in a constantly increasing number of laboratories in many countries, especially in Germany. These kits typically include solvents, columns, internal standard recruitment solutions, calibrators, QC samples, together with a rather brief instruction that is what comes in such a kit. Main manufacturers are Chrome Systems, Recipe, but also Eureka, an Italian company. Waters supplies some kits, but the market is rather limited to few manufacturers at present. As I said, in Germany it's very widely used and continuously wider in its application. To my knowledge, in the US it's rather uncommon, the use of kits. It's important to note that these kits are applied on general purpose instruments from different vendors. So LDTs and kits are applied on the same instruments, which have the same level of complexity to handle. In terms of metrological traceability, manufacturing of calibration materials in the industrial setting of, let's say, Chrome Systems, for such kits is likely to lead to a higher level of patient safety due to standardization when compared to manufacturing in-house such calibration materials. I think this is very likely to be the case. Note that in the European Union, IVDR requires the use of such IVD CE certified materials, calibration materials, if available, from 1928 on. Also, please note, IVDR, it's a big topic, does not regulate in-house measurement protocols. It does not regulate them. It only regulates manufacturing of material devices. According to Article 2 of IVDR, only manufacturing of calibrators, QC materials, reagents, and instrument is regulated by IVDR, but not methods, not protocols, not tests. LDTs are not regulated by IVDR. Yes, despite these kit solutions, it's still the fact that performing LC-MS measurements in the setting of the routine laboratory remains really a major challenge for diagnostic laboratories, especially hospital laboratories. And we all have to note that the number of potential sources of errors that can lead to really wrong results, incorrect results, it is much higher compared to today's standard systems used in clinical chemistry or immunoanalysis, and this is despite the use of these kits. Kits make life easier with respect to manufacturing calibrators, but the handling of the instruments remains the same. These are the same instruments. And even a seemingly simple assay only with protein precipitation, if you look into it, it is a highly complex multi-step process with handling of volumes in the microliter range, transfer of aliquots into at least 2 separate containers, programming the sample list, placing the vials in the autosampler, the management of the mobile phases of the columns, then the processing of the primary data, interrogation of the chromatograms, run review, data transfer to the LIMS. These are very complex processes which can not at all be compared to what is going on with the commercialized photometry assay, for example. It is really, really complex. And a very crucial point is that there is no positive sample identification, no process tracking, as it is the standard in clinical chemistry routine testing at present. In state-of-the-art configurations like this, there is a continuous tracking of the samples from the sample entry over the analyzer systems until sample storage. The sample is always tracked with a barcode on it, so there is the number of actions that can go wrong. The source of errors from the handling side is very, very limited in these configurations, and this is very different to application of mass spectrometry in a conventional format at present. By principle, of course, and we have learned this morning, the technology is very reliable, and based on this isotope dilution mass spectrometry principle, even so, using this technology, the number of potential errors, sources of errors is very high. For example, loading the samples to the autosampler, this is not controlled, there's no positive sample identification. This can go wrong and this will go wrong. And there is no difference between LDTs, kits, self-developed tests and kits from the industry. So it's the level of risk and the number of potential errors is similar or equal if you use kits or in-house tests. So only think of placing a sample in a wrong position in the autosampler, all the principle of isotope dilution will not help. The result will be wrong. And this can happen, and therefore it happens around the world every day. On the other hand, certainly in specialized laboratories, in general, the results are reliable, but we should be aware of the high number of potential sources of errors in this complex workflows in mass spectrometry. And indeed, it is a high-risk process, especially if you think about TDM, where really dosing of drugs, of highly active drugs, is guided by results of such complex testing. And this is especially relevant if you consider the globally increasing shortness of highly skilled laboratory staff. The work is very, very complex. There are less people, less specialized people, which are able to handle such complex processes in the clinical laboratory worldwide. And also I think we have to realize and admit that during the past quarter of a century, I started, as I mentioned, in 1999 with mass spectrometry. From the side of the MS manufacturer, there was hardly any progress with respect to user-friendliness and practicability. The instruments, the handling hasn't changed at all. Automation came in, that's correct, but it was also available in 1999. It's not really new. These instruments were available at that time too. And indeed, automation can increase sample throughput, can also reduce the number of failures during sample preparation. And this is true for both kits and LDTs. And indeed, hand-on time is reduced, can be reduced, but on the other hand, this is an additional very complex instrument which has to be maintained, trained, and so on. And this leads to the point that at the end, the complexity has even increased with automation. Throughput is better, but the complexity for the bench technician becomes even higher with automation. And for these reasons, I think quality assurance systems of clinical laboratories really have to focus particularly on training, competence management, process standardization, the analysis and processing of raw and metadata, instrument performance monitoring, result confirmation, and this is in addition to the standard tools of internal and external quality assessment. So quality assurance for mass spectrometry is complex and is very demanding because the technology is very demanding. With respect to kits, to commercial solutions, they do not really make the assays simpler. They help a lot because manufacturing of calibration materials is not necessary anymore. But the day-to-day, the everyday handling of the instruments doesn't become easier by these kits. Consequently, as an answer to the title question, the quality system requirements to show handling of LC-MS MS analyzers at an acceptable level of risk is not different between the use of commercial kits, CE kits, and LDTs. This is my statement at that point. Many of you probably know this document. It's an excellent document, and I think in the next presentation it will also be addressed. It is on how to do mass spectrometry, very, very helpful, with a very strong focus on method validation. And indeed, method validation is important, but it's always a snapshot under very controlled pre-routine conditions, which can predict to some degree how the system and the assay will be performing in a routine application. But this is, as I said, only pre-implementation. With respect to ongoing application of these methods, I think we really have to develop specific concepts for long-term safety of clinical mass spectrometry application in the context and in the setting of clinical laboratories, with this continuous and increasing threat of limited availability of really highly trained staff. This is our challenge. Regarding management of processes in a laboratory, a very important and worldwide used document standard is ISO 15189. Medical laboratories requirements for quality and competence. Focus of the standard is on things like training, onboarding of new co-workers, management of competences, structured management of non-conformities, of errors, management of documents, how should a SOP look like, what should be the content of SOP, team meetings, management of interaction of communication in a laboratory, internal audits, and so on. So it's process-oriented and clearly not specifically focused on mass spectrometry. It's very generic, the document. It can be applied to genetic analysis, to microbiology analysis, also to mass spectrometry, but it's not specific for mass spectrometry. I'm convinced that we need document standards for that aim, specifically for the complex technology of mass spectrometry, with a focus not on pre-installation validation, but on validation of analytical runs and individual analytical results. Validation means declaring a result or a series valid. So it is a process that takes place every day, every working day, and for every sample you declare it valid for clinical use. This is validation, continuous dynamic validation. And for this aim, we developed this document, a standard. Judy Stone from San Francisco and me. It's published in Clinical Mass Spectrometry, now Journal of MSACL. And in this document, it's a very extended, very detailed document, and indeed we identified and described 32 criteria for this, what we call dynamic validation of series and individual results. 32, it's a large number, and it's really very, very in detail. It's absolutely a golden standard, which is, to be honest, very difficult to implement and to follow on a routine basis for a laboratory. For this reason, we decided to condense this to a set of 9 very fundamental elements, items, which really should be addressed in each series and for each sample if MS results are clinically used. Together with Dr. Habler, which we had this morning, we drafted this document with this list of 9 key requirements for quality assessment, for quality assurance under routine conditions. And at present, we are developing together with the German National Standardization Institute, DIN, in Berlin, to a standard format document, basic requirements for quality management in clinical application of mass spectrometry. This will probably come out next year, and our aim is to translate this, it's called DIN spec, into a ISO standard in the years to come. If it shows value, if it works, then our aim is to develop this further to an international standard. So our community, I think, is very good in protocols for pre-routine internal method validation. This is common to do very good validation schedules for new assays worldwide. I think what we really need in addition to that are protocols for process-oriented long-term quality management addressing the specificities of mass spectrometry, because 15189 is too generic, simply. Yes, we heard 2 hours ago about fully automated closed MS systems. They have been realized. The first instrument, interestingly, was unveiled and presented here in Athens, 1 kilometer away from here at the EuroMedLab 2017. You maybe know that this instrument is not available anymore, but this instrument, as you heard, will be available very soon. And indeed, the handling of these instruments, as you have heard, is similar or identical to the handling of standard clinical chemistry analysis as we know it today, including all the quantification. So indeed, when these instruments are used, there are no quality management. The requirement for quality management, quality assurance will not differ between MS-based analyzers and immunometry or photometry-based analyzers. So in conclusion, in reply to the questions, the question of session 4 as a title is ensuring the quality of measurements for mass spectrometry assays. Is there anything special? And my answer is absolutely yes. It is a very, very complex technology in its present form, and it has very specific requirements for a very good and high-level quality management. And the question related to my presentation, quality systems for commercial and lab-developed mass spec tests, is there a difference? My statement is not really. As long as the procedures are not fully closed and automated, kits, commercial products make life a bit easier, but do not make the processes much easier. So commercial MS kits products make it easier for the routine laboratory, but they remain still a high-risk technology which require a very powerful quality management system. And indeed, fully automated closed systems, they will be a game changer, although with respect to quality management in the MS laboratory. So thank you very much for your attention.
Thank you, Michael, for the very interesting presentation. In reality, here we have a very good method, but with a very specialized instrument that needs very skilled operators, and if something goes wrong, it's very difficult to take care of. But we have to remember that some years ago, even the simple immunochemistry on the microplug photometers with the manual shakers, the manual washing steps, etc., or even a little earlier, the first cytometers with hematology analyzers that you had to pass hours and hours calibrating, adjusting, etc., to have a result that wasn't stable. That reminds me something, and I hope that in the near future it will evolve to much more automated technique. But until then, we cannot still use it, making and taking all these steps in order to be sure about our results.
And I think it's very important to emphasize that fully automated mass spectrometry, I think, has a great future, but the dedicated tests, the specialized tests for new analytes, they will remain. So implementing a very good system for quality management in mass spectrometry application will remain important despite of automation, because automation and high throughput instruments will address large volume tests, but particular strength of mass spectrometry is addressing new drugs, for example.
This is the importance also.
There will be both of
mass spectrometry, that we have a very, very interesting test, a niche test. I was yesterday in France that we are talking about biomarkers for Alzheimer and all of this, the mutated and phosphorylated forms of TOF protein, and the use of mass spectrometry. And these assays are very critical for patients and for future therapies, because now there have already many agents to circulate that will at least control this disease, but without good laboratory follow-up, it's very difficult to administer. So there are questions of the audience? Thank you again. And we pass on the...
We would like to introduce the next speaker, Professor Brian Rappold. Brian is very well known because of his already more than a decade-long role in the setup of ASMS, so that's the Analytical Mass Spectrometry Congress. Also in MSACL, the European variant was in Salzburg until a few years ago, but in the States, and I think I heard also in Asia, it's further going on. And he also is responsible for editions in the TITS textbook. And from that perspective, he will probably talk today about the C62A3, the third version. So we are very curious what this will bring to us, because as we heard from the previous speaker, we need good guidance, and we are already very glad with what Michael presented, but we are looking forward to the next version too. So the floor is to you, Brian.
Thank you, and thanks to the Society and the organizers for having me out. And I'm also looking forward to the C62 revision. Quick disclosures, nothing of real interest here. we'll just jump right into it since we're running a little bit behind. So we had some great talks from Drs. Keevel and Clark earlier on the background of how you do mass spectrometry from a very first principles level. We're going to take a look beyond that, I think to Dr. Burgeser's point. What do we do when we actually bring the assay live? How do we perform quality management longitudinally for a particular assay? You can refer to all of these as sort of background for development and validation, but we're not going to talk about this. You can spend the free time reading. We're going to talk mostly about this, C62, and it is new. We will find out later if it's going to be really improved. It is possibly close to being in the final draft. I think we gave it over to our CLSI handlers about a week and a half ago, so it should be out for public comment. And we do want everybody in the industry, please comment. I will personally be going through and doing the edits and the replies. So the more you give me, the more I don't have to go and work in the lab and do some other interesting things. I want to note here at the bottom, these are the functions that are being realistically changed in a broad fashion. Some of the stuff has minor modifications, but these bits and pieces here are either being more defined or being structurally modified from where they were in the A2 version. We're going to walk through some of those, and this is the landscape of LC-mass spec as we sort of look at it now. This is what we see in publications. This is what shows up when we're doing our validation studies. We don't put a whole lot of thought and effort outside of this scope, because this is the sexy piece. This is how we actually get the assays done. What we don't think about oftentimes is what happens after that the analysis piece. So these are the core components that we've really focused in a bit more on in C62A3. We're going beyond just development and validation. It's what actually happens in the laboratory on a sample, batch, longitudinal process. This is actually really difficult. Can anybody think of a publication where they talk about how they ran an assay for 5 years and told you how they did it? It's not sexy, it's not interesting. You know, we want to hear about the brand new molecule and how we got a p-value of less than 0.005 for this brand new biomarker that's amazing. That's what we read. We don't get, how do you actually run a laboratory? So we did spend a lot of time in conversations and looking for the scant resources available to us to be able to consider what best practice might be in some of these instances. I'm going to walk through a couple of them. They're in the more boldered out boxes. But there are features for each one of these components that are drafted into the new 62A3 that will be, again, out for public review before too long. First principle stuff, peak integration. We do have in C62A3 a statement that we want to have data available because peaks like this are easy. We can't really argue about this peak being integrated right or wrong. But we know that biology and what humans do to their bodies will produce a number of molecules that could be isobaric in a mass spectrometer. So we don't care so much about this being a pretty and easy peak to deal with. We care about the ones that are a bit more challenging. And we also set up some guidelines for how you should be performing things like smoothing functions. So things that we've always sort of taken for granted and or done it in a pastoral context. So smooth as much as you want or don't smooth. There's not been a whole lot of clarity as to how you should treat data after it's been acquired by the mass spectrometer. So I'm going to touch on two pieces here that are addressed in the new 62A3 version related to smoothing and manual integrations. There actually is real data behind how much you should or should not smooth. And if you're doing manual data review, your staff can sometimes have the option of increasing or decreasing the smoothing factors. And that's just a very subjective look at data. There's nothing that we can claim to be objectively in the process of saying, I'm going to smooth to maxima because I want the peak to look completely flat like an LCUV. Or I'm going to undersmooth because I feel like there might be another peak or a shoulder somewhere on the edge of this particular chromatogram. And that's scientist by scientist dependent. We have made a recommendation, and you'll find this in the version of C62A3, and this is coming back from Chris Anke, who, if you're familiar with the development of the triple quadrupole, he was one of the three. They do have some actual science about how much you should be smoothing, and it's related to the number of data points above the full width half max. The math is fundamentally here. There is some disagreement on how many points based on some statistical models, but when you look at the actual values, these end up being pretty much the same. The features of over-smoothing that we see in a lot of data when we're going through and looking at other laboratories' work, and even in our own laboratories within LabCorp, is we tend to lose a lot of precision because people want to make data look pretty. And that is a goal in a laboratory. Your scientists that are doing data review are not much more than art critics the majority of the time. They're trying to define a picture based on its subjective qualities. Does it look pretty? And if you think about definitions for chromatograms, we don't often use the actual chromatographic language to describe a peak. We generally use colloquial terms that describe things as pretty, or it looks ugly, or it's furry. These are all terms that we hear in the laboratory. So we are making recommendations around the number of data points to define the amount of smoothing, and this doesn't matter which sort of digital filter you use for smoothing. It's really regardless. It can be a Gaussian smooth, it can be Savicki-Golay, but the number of smoothing iterations that you can apply are defined from these 3 papers here, spans a range of about 0.5 to 0.7 times the number of data points at the top of the peak, or the top half of the peak. And the reason we're trying to get to more granular detail on this is, again, providing guidance for our manufacturers, for our laboratories to perform more consistent work. Harmonization and standardization doesn't just start at the calibration level and end at the analysis piece. It actually goes all the way into data review and data interrogation. To reinforce the subjectivity component, if we pretend that this is the baseline of a peak, and this is real data, and we're asked to make a determination as to where we would integrate this peak, because we're trying to ignore this shoulder here, because the software that we're using just happens to fully integrate the entirety of this piece. And we're saying, I want to exclude that. And as a thought exercise, you don't have to raise your hand, but just think, is this a good integration? And some people might say, yeah, I could live with that. Or what about this? Is this a better integration? Maybe. Is this a good integration? You could find this sort of integration pretty consistent in some software, these drop downs that cut through somewhere below the noise. Or is this a good integration? Does that actually represent the baseline, somewhere that's supposed to be drawn through the middle of the noise? Or is that a good integration? These are all examples of how people might choose to manually integrate a particular peak. And manual integrations in our laboratories happens a lot more than I think people want to admit. It's just the truth. There are some recent publications in the lipidomic space that claims that they did, in a study of some 50-plus analytes and a number of individual samples, they manually integrated every single peak, and their claim was they did this because it provided better integration reliability. And I'm going to say that again, but I'm going to use different words. They manually integrated the peaks in every single sample to provide objectivity to the data. This paper was published in JASM just a few months ago, which is, if you think about it, it's contradictory. You can't be objective and be manually integrating. It does not work that way. In C62, we've put in some recommendations, and these should not be a surprise to anybody. Don't manually integrate. You don't really know where the lines are supposed to be drawn, so try your best not to. But importantly, if it's low-level signals, just don't. If your assay is not good enough to provide a consistent, objective integration component, your assay is just not good enough. And it needs to go all the way back to development validation. Or it could be that the instrument's not playing very well that day. Your instrument needs to be maintained and corrected. Manual integrations are one of the biggest sources of error that we see, particularly when we're trying to define the concentrations in low response features. And so we do have this, including CALs and QCs. If we're being honest with ourselves, getting QCs to pass is one of the primary goals of a scientist in a clinical mass spectrometry lab. It just is. Not casting stones. I live in a glass house, and I'll break the glass down as well. This does happen all the time. If you can generate a rule set that does not allow the manual interpretation of quality control events or calibrators to be changed to try to fit QCs in, you will have an assay that is what we would consider to be of high enough quality to report data for patients. So we are making the recommendation C62. Try to keep it away from low-level signals, and don't touch the CALs and QCs just to make stuff work. If the assay is out of control, it's out of control. And coming to control, we have expanded our thinking around Westgard rules and mass spectrometry. And it's two important veins I want to point out. So Westgard, when he originally did this, he had a couple of assumptions that worked pretty well for him because he was not dealing with a computer. He was doing this stuff with a stats table and a slide rule. The considerations that he had were it's one analyte at a time, and calibration never changes within a lot. Our recommendation in C62A3 is we want to continue calibration on a batch level basis, or do it frequently enough to be able to capture the variations in internal standard function changes, so we get some equilibration of the IS solutions that will change the response function of mass spec. And the mass spec response functions will also change over time. There's not a mass spectrometer vendor that will claim ruggedness over the span of a mass spectrometer's life or a mass spec assay's life that's going to be worthful for us to not address calibration differences. And this is just the assay calibration, not mass accuracy or mass resolution. This is just, again, the assay concentration-based calibration. I will say that I have had one mass spectrometer that did perform exceptionally ruggedly. It did the same exact thing every single day. And as a laboratory corporation, we have a lot of mass specs, lots of them. We'll process many millions of samples across our network in a very short span of time. And I will tell you the secret to having a mass spec that works the same way every single day, and it's not hard, you can do this at home. If you want it to work exactly the same way every single day, you unplug it. That's all you have to do. And you will get consistent performance of nothing, but it'll at least act the same way every single day. So we are going to look at this in terms of when we calibrate the assay, what's the effect of that in QCs when we do it more frequently. And then, again, going back to Westgard and the original proposition of just doing one analyte at a time, we've got a mass spectrometer. We can measure lots of things in the same sample. And that sort of breaks the Westgard scheme, and I'll show you that in here in a bit. But the first one, if we assume that the instrument that we're measuring on is longitudinally calibrated and the calibration is true, we tend to see plots like this. And this is not a big change for anybody. This is your standard Westgard plot. And I took the colors directly from the Westgard website, so if you're going there for references, you'll recognize the colors. 1SD, 2SD, 3SD. And there's rules associated with each one of those based on this workflow. But if we calibrate on a per batch basis, or we calibrate for every time that we analyze a QC function, we actually lose the variance of calibration values in this plot, because we're getting variance from the quality controls and we're getting variance from the calibration event. And to show you an example of that, this is what your QC plots would look like if you were accounting for the calibration variance on top of the QC variance. And to make the example a bit more, if we follow the Westgard rule sets, we can induce violations of some of the Westgard rules that would reject a batch, but we don't notice that because we're all playing in this model over here. So we have made some recommendations. They're broader because we're not trying to capture the intent of every single assay out there. It's impossible for any guidance to say, if it's this molecule, you have to measure it this way and do this stuff with your QCs. We have removed, as much as we can, some of the cloudiness around thinking about QCs, but we've still left it broad enough for local director interpretation and thoughtful interpretation of the guidelines. Clinically and technologically appropriate criteria are going to be further defined in A3. We are not recommending across the board that you have to use Westgard rules every single time. The historic guidance from FDA and the EU, which is now codified in the M10 document, accuracy and precision within 15% is a pretty good target. And if we focus on the acute outcome of an assay, if all of your QCs are within 15%, that should be acceptable. And you can look at precision as opposed to following the rules from Westgard. Back here, you can look at precision as more of a longitudinal trending and not use these rules to acutely accept or reject a batch. Multiplex QCs, and this is a bit of a complex slide, so I'll walk you briefly through it. If we have 3 quality controls in an assay, and we have 1 molecule, or 10 molecules, or 50 molecules that we're measuring, these bars or these lines represent the propensity for failure based on the standard error. What this is showing you is that as you increase the number of analytes in a panel, and let's say you're doing amino acids for inborn errors of metabolism, or acyl carnitines, or quantitative organic acids, or you're trying to do a quantitative toxicology panel, or I think to Dr. Keeble's point earlier, it's not really useful to run a massive steroid panel, but should you so choose, if you follow Westgard rules, you shall fail every single batch when you get above about 47 analytes. It's just statistics. We can't argue the numbers. Now, we can make those batches pass, going back to our manual integration attempts. We can force things in, but in the instances of running this many compounds or more, you have to fail Westgard, which means that multiplex capabilities in mass spectrometry is being held back by our standard thinking around Westgard rules and quality control. The language that we put into C62A3 around this content is a bit more vague because there's not a body of literature yet on how to manage quality controls in a multiplex environment using more robust statistics. But we do have hope that our colleague Stephen Master, who's been working on this for a number of years and addressed this in publications for multiplexed immunoassays, will be able to come up with a framework for us to start to develop more stringent or more specific guidelines for treating multiplex QCs. Now this does allow us for applying the M10 rules of fixed 15 or 20% the LLOQ if you so choose, which means that overall your assay has to be pretty good at the low levels, but it shouldn't fail outside of the normal rate of failure. We do have some functions written into the documents that if a molecule is correlated to another molecule by function of physiology or biology, those shall fail together if one fails. But it doesn't mean that the entire panel is now being rejected. There's a couple considerations for this in that document. So quality assurance is an important piece, and I do like immunoassays when they work. The trouble is they don't often work. It's good for some clinical indications, like if we're trying to measure a whole body of proteins that are within one family, you can get a pretty reasonable number. The specificity of mass spectrometry precludes a lot of good immunoassay components being applied to mass spectrometry. So when we have data that we can look at, and this is really what separates mass spec from immunoassays, it's not just the internal standards, which are great, beautiful things. This is what really separates mass spectrometry from an immunoassay. Because what we can do is we can review this list of components, and this is just a couple of examples very similar to Dr. Bogesser's content from 2023. These are all examples of things that we can look at beforehand to determine the fidelity and the veracity of a result before it gets reported. The only time we know an immunoassay is really wrong is when we get enough complaints from a physician saying, your result does not match my presentation. None of this makes sense. That's the only time we know, and that's after the fact. I oftentimes refer to mass spectrometry as being a proactive component when it comes to quality assurance, and we have done a lot more in outlining that content in C62A3, saying you really should review these components specifically. And in a few cases, we've set some tighter boundaries than what they used to be. So for example, the internal standard recovery in C62A2 was 50 to 200%. We've shrunk that down for logical reasons. 200% would indicate a double aliquot of the IS. If you think about the volume, you never actually get to a full 200%, so we've dropped that down to 180. And in similar thinking, 50% loss of signal should indicate some significant issues, so we've raised the threshold to 60 to 180% for IS recovery as one example of a metric that we've now better defined. We've also updated a lot of content on the ion ratios. We've drafted out specific recommendations for how to calculate them and when to utilize them based on how you calibrate, how you use quality controls, and the clinical indication. So there's a bit more structure around how ion ratios should be done. Now, I will say that there's very few literature references for ion ratios. So it was much more of a poll amongst the document committee as to what you actually do in practice in your laboratories. Let's not theorize this. Let's pull your SOPs, and let's talk about what you're actually performing, as we're supposed to be the people guiding the industry, the best of the best. We're going to take what we actually do and not just theorize this stuff out. This is a table from a publication I had back in 2022 that does discuss a lot of the features, again, very similar to Dr. Bogesser's content earlier. And just to say that it's not us speaking and proselytizing, a lot of this was actually derived from work that came out of Irene Vanderburg's journey in Jenny Van Eyck's lab back a couple years ago when she was at Cedars-Sinai. So we're not just saying this because we think it's the right thing to do. We do it in our laboratories, but it's also been utilized in other folks' laboratories as well outside of the document committee for C62. To shift gears a little bit, and this is one of the more difficult topics to get into because we didn't draft a whole lot around this in C62, but the quality assurance features for LC-MS are oftentimes human-based. We're trying to use humans as the ones to block out bad results and kick forward the good results, and that's a challenge. And I just want to highlight a couple things here that the reality of what laboratorians and data reviewers have to go through is quite significant. And we have a lack of attention budget. So if you think about the number of features that people have to recognize and then compare, oftentimes to a calibration scheme or a quality control chromatogram, the number of visual components they're supposed to keep in their brain, plus any numeric outcomes that might be meaningful, like is there carryover, or what's my internal standard recovery supposed to be. This is a lot of stuff for one data reviewer to remember. And that really does affect our quality because much like goldfish, we have very bad short-term memories, and the number of individual features that we can retain as we look at data is about 4. That's the normal person can remember about 4 different features out of this whole list as I can identify a difference here going through hundreds and hundreds of chromatograms. We also have to unlearn data review components. So if I'm going from batch to batch to batch, or assay to assay to assay, I have to forget the last batch or the last assay before I start the new one. And that's incredibly difficult, incredibly difficult. And there's also a thing that we've been addressing a lot in our laboratories about error fatigue. So if we set up an automated system to look at data, and the data is intended to flag errors, if those errors are constantly flagged but they're not really errors, people will stop looking at them. So it's great to have flags, but those flags have to be validated and moderated in a way that we don't have people constantly looking at bad data and ignoring it, or looking at good data and kicking it back down to be reanalyzed. The middle road here is, it's tough to find, and it takes a large amount of data to actually get to not having error fatigue in terms of data review and looking at bad chromatograms when they're actually good, or good chromatograms when they're actually bad. If we think about the mass spec experiment as a whole, the entire assay, only one point in the entire series of operations are we actually concerned about accuracy, and that's when we prepare calibrators. Everything after that is precision-based. If you have an SOP that says, I'm going to do 50 microliters of sample and 50 microliters of calibrators and 50 microliters of QCs at the beginning of your first aliquot, great. But it also still works if you do 40 for everything, because that's a precision-based experiment. As long as the concentration of the calibrators is as true as you can get it, that's all that really matters, and it's precision all the way down. When we come to maintaining precision through an assay, that's relatively easy. Just do the same thing every day. We can automate that. This part here is where we start to see drifts in harmonization. And if we're running proficiency standards or proficiency tests frequently, we can sometimes pick up on inaccurate calibration preps. One of the things that we put in is making sure that you don't have quality controls and calibrators prepared in-house for a lab-developed test at the same time, because you run the risk of error not being observable. So, co-preparation of these critical materials that define our accuracy is not recommended under any circumstances. And you also want to have time for error correction. We do find that some laboratories, if you get in a hurry, it's easy to sort of have a fudge factor to make things work. And the goal, I think, for clinical laboratories is not to make things work, it's just have things work. And that is a different mindset from how laboratories will sometimes operate. And this is another new piece that we've included as part of the appendix of C62A3. And the story behind this is actually a bit interesting. And I think if you've done a validation experiment or if you've done qualification of new materials, you'll appreciate how useful this could be. So whenever we do a sampling, we generally consider that the mean is going to be representative of the population, and we have a Gaussian distribution when we do analyses. And that's pretty true, but the majority of the time we're not considering all of the variance that goes into a process. And we're not considering how true that could actually be. So there is it's an older document, but there's a way to calculate the CVs, or the coefficient of variation, of a CV. And I'm highlighting this, if we think about our loosest terms, where we don't have biological variation to define the total allowable criteria, we can refer back to M10, which is a 15% plus or minus, or a 20% plus or minus precision and inaccuracy target. If we only measure a small subset of components, and be this in validation or in qualification of a new material, just because we're within that 15 or 20% target doesn't mean that we're actually going to be good enough to maintain that 15 or 20% target over time. So this table, if we just reflect at the numbers of samples that we would measure, and this is the 95% confidence interval of the coefficient of variation, if I really want to have a CV less than 20%, but I'm only measuring 5 replicates, my actual CV needs to be less than 8%. If I'm measuring 15 replicates, and I want to guarantee that for the assay I'm performing will have a reasonable response rate where I really do catch my random errors and my systematic error is going to be observed, if I'm doing 15 replicates in validation for, say, an intra-assay and precision study, my actual CV that I measure in validation should be less than 12% to ensure that the majority of my population, when the test goes live, will be less than 20%. This makes sense to everybody? Sort of. We're trying to find some boundaries so that when you take an assay through validation, or if you're qualifying a new lot of material, you don't underestimate the actual error, and you don't propagate an assay that's going to have a lot more imprecision than it really ought to. And again, using that 20% criteria as a sort of basement of how good you should be. You have to be better than 20% plus or minus in accuracy and in precision. And this is a way to maybe perhaps better frame expectations in validation so that when we release that assay into the wild, we know we're going to have a pretty good chance of having all of our results be within 15 or 20%. To try to keep it short, we have a lot of opportunity in mass spec, and I think to Dr. Vogischer's point, we have to treat it sort of differently. There are going to be some distinct components that we don't just get the sensitivity, we don't just get the perceived specificity of a mass spectrometer, we have all of these additional quality gains, and we have to consider mass spec to be distinct from other technologies. It's nothing like an immunoassay, it's nothing like an LCUV, it's nothing like an ECD assay. When we do a quality management plan for a mass spec assay or for a mass spectrometry laboratory, those have to be put into place. We're not going to be able to use the guidance from 15189 to define mass spec specific things. We get sort of the feel for what they're talking about, but again, mass spec is so specific and special that it needs to be considered as a separate unit within the clinical laboratory's quality management plan. And when we look at data, and to come back to my point of mass spectrometry having the opportunity to be a highly proactive quality scheme, there's an enormous amount of data buried within a chromatogram from LCMS or LCMS-MS, a huge amount. And every bit of that data should be taken into account when we're trying to provide the highest quality result for our patients. The group at LabCorp helps me out a whole bunch. You guys probably know Russell, and a number of you know Gregory Jans as well. And then the document committee, not everybody's listed here, but the folks that really have put in a lot of extra time and heart and effort. So Dr. Bill Clark is here. Reynold Julian, Stephen Master, Gwen McMillan out of ARUP, and then Andrew Hoofnagel out of University of Washington have all been absolutely essential in trying to get C62A3 wrapped up. And with that, if you have any questions, feel free to email me. If there's any negative criticisms, please email Bill Clark at clark@johnhopkins or jhu.com. And I've got some time for questions.
Thank you very much, Brian, for this quite provocative lecture, I would say. I do have one question, if I may, regarding the standardization. Is anything mentioned in this A3 document on the type of calibrator? For instance, for quantitative proteomics, could you use peptide-based calibration versus intact protein calibration? Yeah,
there's a document for that, and that's C64. We didn't touch proteins at all. And then in C64, they had the same conundrum, is that what is the measurand? And are the calibrants representative of the measurand if you're doing peptides, and then you're using the protein as the actual reported out feature?
Yeah,
that never really landed in C64 very well either, so it's still a point of contention. I think it will take a lot more discussion for everybody to feel comfortable with the language as to what you're measuring, if you have to do an intact protein. And I think that the challenge for intact proteins, to sort of take a left turn here, I don't know that we're ever going to get to a real good protein-based calibrator, just given how every protein can perhaps be a distribution of various subforms or isoforms. And I think the example for my liking is thyroglobulin, which is tons of assays have done thyroglobulin by mass spectrometry to avoid the autoantibody component. The calibrates that we've seen, so say Sigma Aldrich's, it's the intact protein. But you know what it doesn't have that natural thyroglobulin has? A ton of iodines. Mm-hmm. It's not there. So the calibrant that we might have available to us is not going to be the biological feature. And if we go one step back to the certified reference material for thyroglobulin, that wasn't really thyroglobulin from human blood. That was a bunch of mashed up tissue that the isoforms did not match what we have circulating. So the philosophy of calibration in protein-based assays, I think, is going to be one that you pick a side and you fight for it, but we're all going to end up in the middle, which is pick something, call it what it is, and measure that. No specific guidance.
Okay, I think we can have very long discussions on this. Thank you very much. Are there any more questions? No? No. Then, Brian, many thanks.
And we arrived now at the final presentation of this fruitful day. It is Hubert Breisfeld that will present about EQA and formal standardization programs, tools and services available to laboratories to improve and maintain quality testing on the context of mass spectrometry always, and I don't think that we have to focus on the excellent work that Hubers is doing during CDC about the standardization of cardiac markers, of hormones, and also at the level of technical committee 212 of ISO in production of standards that have a relation with reference laboratories. So you have the podium.
Thank you, and thank you for staying with us so long for this session. My talk is about EQA programs and formal standardization programs. I don't have anything to disclose, and what I try to accomplish here with my session, everybody knows what EQA programs are, but there's probably some heterogeneity, if you will, in the understanding about standardization programs, and let's hope that we can put some light in there. So before we start, the definition of EQA programs, as it is stated in ISO 17043, is an evaluation of a laboratory performance or an examination of samples from external origin for the purpose of determining the adequacy of a laboratory's pre-examination, examination, post-examination activity. And let's see, forward, this one. So the main focus really for external quality assurance program is to assess the overall performance of the laboratory, including the pre-analytical, the analytical, and the post-analytical phase. Now, for standardization, I was not able to find an official definition, so I just used the definition we use at CDC. And to us, standardization is a continuous process in which relevant analytic performance parameters of a laboratory test are improved and maintained in a manner that measurement results are comparable across methods, location, and over time, and meet certain clinical needs. A couple of things to highlight here. Standardization is a continuous process. I sometimes hear statements like A1C is standardized, which implies that, it's a finished process, there's nothing else to do. While in fact, we need to continue assessing and improving the quality of A1C measurements because assays change over time, new assays come on the market. So it's a process. Standardization typically only focus on the analytical performance, not on the pre-analytical and post-analytical issues. And it needs to meet certain clinical needs. I also want to point out EQA programs are sometimes also called proficiency testing programs, and some people see subtle differences. For the purpose of this presentation, you can use EQA and PT programs interchangeably. Also, there is a special version of standardization which is called harmonization. The underlying principles are the same, so for the purpose of this presentation, you can use standardization and harmonization interchangeably. Now, in EQA program, there are different activities, and when I looked at different EQA programs, the way they are operated and designed is somewhat different, even though the overarching goal is the same. And so, EQA programs create and distribute samples, and sometimes they're highly modified samples, or what we also call non-commutable samples, but they're also commutable accuracy-based surveys available with reference values assigned, or also without reference values assigned, where just the group means are being used for evaluation. As I already said, the evaluation is often based on peer groups, so you only have to be as good as your partner laboratory that uses the same type of assay that you're using. But some EQA programs also make comparisons to a reference value. All of them provide data so the laboratory or participants can look how is my particular assay performing to other assays from other manufacturers. And most of the EQA programs also focus on education. trying to provide information about the data that were collected in the program to help with the interpretation of the result that the participant reported, but also to provide an overall picture about the variability of assays across different platforms. So education is an important component in most EQA programs. With standardization, it's a little bit different. Standardization programs have multiple components. From these here, what I'm listing here are the components or activities conducted in CDC programs. The first one is to create the tools required for standardization, which is basically developing reference methods, reference materials, but also assessment protocols as they're described in CLSI documents and other places. But developing a reference material, a reference method, does not do anything unless you use it. So somebody has to apply these tools and assess the performance, certify the performance, or perform some sort of validation, also monitor the performance over time. And the monitoring part sometimes is also done in collaboration with EQA providers and their accuracy-based programs. The second part, which becomes more and more important, is that once we have these tools, the assays standardized, we also need to make sure standardized assays are integrated in the framework of the laboratory medicine. So we need to make sure that we also have reference intervals that are based on standardized assays. We need to have cutoff values that are used in clinical practice guidelines based on standardized assays. And now becoming more and more important with these big data hubs that are created across the whole country with laboratory data feeded in. We need to make sure these data are comparable across systems and time to make sure they are in what people call interoperable. Sometimes people say that we standardize our assay by being compliant with ISO 17511, which is about metrological traceability. And I just want to point out that establishing metrological traceability is only one of several activities in a standardization effort, and we'll talk about that a little bit more in the next slides. So when we do standardization, we can in our programs you can do two things. You can help with establishing the calibration accuracy. So this is basically the traceability chain is a different format as it is described in ISO 17511. And what the standardization programs like the CDC program or the IFCC A1C program is doing is helping manufacturers with establishing calibration traceability. So they basically help calibrate assays in an appropriate way. But what we also do is we help to verify the calibration by providing the tools or the procedures to assess whether the calibration was done appropriately. And we can do this through reference laboratory networks. They have their own calibration activities. We do this through manufacturer certification and also through accuracy-based EQA programs and monitoring programs. And establishing traceability and validating traceability are both requirements of ISO 17511, and standardization programs help laboratories and manufacturers with that. So for EQA programs, the main customer, if you will, are clinical laboratories. While for standardization or harmonization programs, it is really the test manufacturer or the laboratory developing lab-developed tests. And the reason for that is, for one, the fully automated systems that have been talked about today is something that the laboratory cannot really change or improve. So if there's a problem with a clinical analyzer, the manufacturer needs to fix that problem. The laboratory typically does not have the ability to do that. And also what we try to achieve with standardization is that the instrument is already accurate and well calibrated before it leaves the manufacturing facility, so the laboratory does not need to worry about that. As we already said, the EQA programs look at the overall performance of the laboratory, while the standardization programs really look at the analytic performance of a particular test. And so with EQA programs, we do comparisons to peer groups or reference systems. With standardization program, the assessment is always done to a reference system. And so the grading is based on fixed criteria, while with the EQA programs, it's depending on the program, it can be based on statistical parameters like simple case standard deviation, or also on fixed parameters. And if you look from a study design point of view, EQA programs are always cross-sectional. They provide a snapshot in time, but typically do not provide information about performance over time. Standardization programs can be, depending on the type of program, can be both either cross-sectional, making an assessment at one point in time, or look at longitudinal data. And there are, successful participation is typically required. Successful participation in EQA programs is typically required for EQA program. For standardization programs, there are no requirements. So it's really up to the manufacturer or laboratory operating lab developed tests to participate. Okay. And because the focus or the intent is a little bit different between EQA programs, so it's also the design. If you look around at EQA programs that are available in the world, they offer between 2 and 12 challenges per year, with very few samples, 2 to 5 samples per challenge. As I said, scoring is per challenge, and they typically use pooled modified specimens. Standardization programs are conducted, the assessments are conducted less frequently, 1 to 4 times per year, 4 times per year maximum, use more samples, and you can use up to 4 consecutive challenges to assess the analytic performance. And most of the programs really use single donor specimens when performing the assessments. And there are also some practical considerations. EQA programs sometimes need to provide samples to over 1,000 laboratories, so you have a lot of specimen needs. That's why you need to have pooled materials. While with standardization programs, we deal with individual manufacturers, we can use single donor samples much more easily. So the reason, that's another reason why we have pooled materials with EQA program. Now, the process and how you deal with EQA programs, you know that all very well. You send you get samples, you send the results back on these samples. The EQA provider evaluates them, and you get an evaluation report. And then it's up to the laboratory to look at that report. And if there's an unacceptable result, the laboratory has to initiate corrective actions or preventive actions. And this is just one example from the College of Plant Pathologists in the US, a report on testosterone, how the information looks like that a participant gets. These are the 3 samples, reported results, the mean of all mass spectrometry assays, and the allowable limits. And everybody, of course, is looking whether, there's the word acceptable in there, and everybody hopes there's no unacceptable. There's also information provided about other peer groups that are used in this particular case. The means of the peer groups ranges for this particular sample from anywhere between 460 to all the way to 930 nanograms per deciliter. So people get an idea, how their peer group looks like in comparison to other peer groups. The thing is that, the laboratory is really responsible to figure out, if there's an unacceptable result, what is the source of the result, and needs to do some investigations. EQA providers, but also in the literature that you find some guidance on how to approach that. at the end of the day, EQA programs are very good in identifying a problem, but they do not provide any information what the problem might be. Standardization programs operate completely different. Typically, what we do, what is being done is in a first phase, samples with reference values are provided to participants. Participants can make their own assessment or work with the program provider to figure out what is going on with the assay, make adjustments, and then once they feel ready, they would enroll in a second phase where they get blinded samples. They would need to analyze them. These blinded samples are then assessed by the program provider, and a certificate is issued when the program meets the criteria. And we had situations where participants only perform in phase 1, never moved to phase 2, and we also had situations where participants started with phase 2, never did phase 1. Everything is possible. It's really up to the participant to decide how they want to approach that. The highest success rate, of course, is when you start with phase 1 and then move to phase 2. Now, as I mentioned, in standardization programs, typically single donor samples are being used, and up to 40 are typically used for evaluation. By having 40 samples, it really, over the analytical measurement range, we really get a good information about the analytical performance, not only at a few points, but across the whole measurement range. And by using individual samples, we don't have to worry about non-commutability, because a single donor sample, by definition, is commutable. We also always look for replicate measurements to get information on imprecision in addition to bias. And we perform quarterly assessments to get information about the consistency of the analytical performance over time. We also work very closely looking at the data to make sure that, for one, we only provide samples the assay can actually measure. There's no point in providing samples that are below the measurement limit of the assay, but also to identify clerical errors. And with EQA programs, as well with standardization programs, the majority of errors that we observe are just data entry errors, clerical errors, either putting the numbers in the wrong unit, or missing a decimal point, things like this. So we try to make sure that these kind of mistakes are taken care of. So when we talk about the analytical performance, it's really the analytical performance, not the performance of the person entering data. And this is a snapshot of the information that we collect and that we also provide to the participants. These are data on 40 samples. Each symbol represents the mean of 4 replicate measurements. In this particular case, testosterone, data on testosterone from a participant. And if you look at the data on the higher concentration, they are reasonably well scattered around the zero bias line, with an overall mean bias of 0.3%. So these data indicate that this assay is probably well calibrated. But if you look at the lower concentrations, we do see quite some scatter with a lot of positive bias. And a pattern like this typically indicates that there is a lack of selectivity. So there are some interfering compounds that become more prevalent at the lower analyte concentrations. And also the mean bias for the samples in this concentration is much higher. So this assay is well calibrated. It is traceable according to 17511, but it does have measurement problems at the lower concentration range. And you can only get this kind of information if you have a sufficient number of samples covering concentration range. If you only have a few samples from an EQA program, you most likely would not be able to identify what the source of the problem is. The other thing that we do is we look at 4 consecutive quarters for evaluation. So if you enroll in the program, you have to wait 4 quarters to get your first certificate, but then you get certificates every quarter. And we found that quite helpful based on data that we observed in our program. So this is one participant. Again, it's a testosterone assay, lab-developed test. And at the beginning, this assay actually performed very well within the criteria, and then all of a sudden we see this wild scatter going on measurement bias, and upon further investigation, it turns out it was an operator problem in the laboratory, so the operator was trained accordingly, and the performance went back to where it's supposed to be. But then we saw this trend going up to higher measurement bias, which turns out to be a calibrator stability problem that the laboratory had. So by having these longitudinal data, it's very helpful to identify problems. I want to point out that the problems that we saw over here were not caught by the laboratory's quality assurance systems nor by EQA providers. Another thing, when we look at the operation of EQA programs and standardization programs is the use of pooled materials. And of course, pooled materials are more economical in terms of an operation, but the question is, do they provide the information we need if we want to improve measurements at the patient care level? And so what we did here is we took 5 individual donors and created a pool with these 5 donors. So shown here is from one laboratory for vitamin D. They measured these 5 samples. We saw a bias over here. Based on the way we created the pool, we would expect an average bias over here, but what we actually saw is a 0 bias. So we would not, in this particular case, a pool would not identify any measurement bias with this particular sample, in this particular situation. And we did this for 5 different pools and also a number of different laboratories. And what we saw is, for one, the variability in measurement bias when using pools is much smaller than what we see with patient samples. And we typically cannot predict what the measurement bias is in a pooled material based on the bias we see in individual patient samples. So to really assess the analytic performance of an assay, make sure that they measure correctly at the patient care level, we really need to have individual donor samples to make assessments. I'd like to point out that this observation is done with vitamin D. We are currently looking into additional experiments to see whether observations like these also apply to other analytes. And so the big question is, how does standardization programs and EQA programs fit with each other? And I think there are different ways to describe it. One way to use standardization programs and EQA programs together is shown here. At the development phase, it's good to have a large number of samples with reference values assigned. So at the development phase, the developers can already make sure that measurements are accurate. Then once the method is developed in production, phase 2 is very helpful to make sure that the analytic performance is maintained and to be able to identify problems such as lot-to-lot variability. And if there are problems, phase 1 samples can be used to further investigate and mitigate the problem. And then in the last stage, we want to make sure when we standardize an assay that this improvement really shows in the patient care level, and EQA programs are, especially accuracy-based EQA programs, are ideal to verify the analytic performance of the assays. And again, if there's a problem that is related to the analytic performance of the assay that turns out that shows that the EQA program, phase 1 samples can be used to further narrow down what the specific problem is, whether it's a selectivity problem or a calibration problem. And so what I try to point out with this slide is that EQA programs, especially accuracy-based EQA programs and standardization programs, complement each other. And together, I think we feel that they provide a comprehensive package of samples and materials that laboratories and test developers can use in order to assure the accuracy and reliability of the assays. So in summary, EQA programs aim for improving the whole laboratory performance, from the pre-analytical to the post-analytical phase, while standardization program really focus on the analytical performance of the test systems. EQA programs typically only can identify that there's a problem, and it's up to the laboratory to figure out what the problem might be. And while standardization programs aim on providing data to help identify what the problem might be and then help directing activities in this direction, because as I showed, if you have a selectivity problem, you don't need to fiddle around with calibration. You really need to figure out what is the specificity, how can I improve the specificity. And so the last question is, how many standardization programs are there, standardization activities are available, or how many EQA programs are available? And especially on the EQA programs, it's a hard question because you really have to search around. I think the IFCC Scientific Division website is a very good first place to go to obtain information about standardization activities, but also about activities related to EQA programs. And, of course, those interested in what the CDC is doing or what's going on with A1C, these are the two places where formal standardization programs are ongoing. Feel free to visit the website. In the US, we have CMS, which is the agency that regulates clinical laboratories. They have a website with all the proficiency testing programs that are available and certified by CMS. For Europe, Equalm is a good source of information as well. And with that, I'm at the end of my presentation. I could only scratch a little bit. We at CDC have a new symbol for our programs to illustrate that standardization is more than just calibration, and there's a lot of activities going on really to try to improve the accuracy and reliability of tests. And with that, I'm at the end of my presentation. I thank everybody for staying with us for such a long time.
Thank you, Hubert. Remind us the principles of EQA and standardization. It's really very important. The problem with EQA is you have to use commutable material, and commutable material based on single donor, fresh, untreated sera, and nothing else, even not frozen. So, from the other side, if you are talking about standardization in between assays, you are talking always for the same generation, same family instruments, and maybe same lot reagents. Otherwise, we have other problems interfering. Okay, to say the truth, I think EQA is good, but if you try to use pooled sera, that is the normal material, you have to consider each family of assays that you are using separately, and try to find in these families if each laboratory performs well. Because if you try to compare in between different families of analyzers and instruments, I don't think that it will work. But anyway, have we questions? Okay.
Thanks for the great presentation. I have a question regarding the acceptance criteria for the EQA program where you have a reference value. How do you set them?
Yeah, so the criteria used in standardization programs are typically based on clinical needs. The way we identify clinical needs is by just asking the physicians, how good does your assay need to be to, diagnose a person with hypogonadism, for example. And then that drives the way we set these criteria. So it's based on consensus, but also based on practicality in some cases, because some physicians may say, I want to have zero bias, and then we need to educate them that something like that doesn't exist. But in general, we also are being approached by the medical community, Endocrine Society, for example, and those kind of organizations saying, we have these guidelines, we cannot use them in patient care because of the variability. Can you help us? And then that's how the dialogue starts. The other thing is that these criteria are not fixed criteria because guidelines change. We just have now a situation where we still work with guidelines for cholesterol and HDL and LDL cholesterol that were developed 30 years ago in order to support the old NCEP treatment guidelines. We have now completely new guidelines that focus on very low LDL concentrations. And so what we need to do is we need to adjust these criteria to make sure they are in support of these new guidelines. So yeah, these criteria are based on requests or based on dialogue we have with the medical community. And the other thing that is important is they are not forever. They will change as the needs change.
Okay, thank you.
Other question? I think that we finished for today. Hope to see you tomorrow morning, where we will start at 9 exactly in mass spectrometry as a new tool in laboratory portfolio. It is value for money. I think that is a very interesting issue. So see you tomorrow morning.